Hello everyone, February 11th. Alright, so last night I got stuck. I got stuck with this. Didn't know how to do it. I thought about it. I still actually have no idea, so I got annoyed. I decided to just use NumPy, and then I passed, but terrible time. So that's not the right way to do it. I think I have to check the hint. I really think that my solution was right, but yeah, it was not so. We'll check the hint and see where we got wrong, but probably not today because I have other things later today. So let's just finish this and then call it. Minimum fuel cost to report to the capital. There's a tree with no cycles. Yeah. Structure. Country network consisting of n cities, number from 0 to n-1, exactly n-1 roads. The capital city is city 0. You're given a 2D integer. Have I done this before? This looks familiar. Roads. There exist a bidirectional roads from AI to BI. There is a meeting for the representative of each city. The meeting is in the capital. There is a car in each city. You're given an integer seats that indicates the number of seats in each car. Yes, I've done this before. A representative can use the car in their city to travel or change the car and ride with another representative. The cost of traveling between the two cities is 1 liter of fuel. Minimum number of liters of fuel to reach the capital city. I don't remember how I did it though. Let me get my pencil down. Okay, I need to read this question again. Actually, I don't quite understand. So we have a city, so they're connected. There's a meeting at the capital, which is 0. There is a car in each city. You're given integer seats that indicate the number of seats in each car. A representative can use the car in their city to travel or change the car and ride with another representative. The cost of traveling between two cities is 1 liter of fuel. So in this case, seats of 5 need 3. The time to 1 goes directly to capital. Yeah, 1, 1, 1. But here, seats is 2. Essentially 2 goes directly from city 3 with 1. Oh, 2 goes here. And then 2 and 3 goes together to city 1 with the 1 liter fuel. And 2 and 3 goes to capital in 1, so that's 3. And then 1 has to go by itself, that's 4. That's 5. That's 6. That's 7. The rest needs to go, so it's 0. Yo, I remember this one, but I forgot what the method is. Well, it's a tree, right? And then we can start from edges, okay? So from edges going in, okay? From edges going in, and once, yeah, because the representative on the edges has to go in. And once they go in, they might as well just band together, because otherwise they have to go the same way anyway, right? They have to go the same way anyway, so there's no point not to sit together. So go from outside, we're gonna go in, and when we reach there, we can count the number of people. If it's smaller equal to the seats, then they can keep going, right? Just count another once. If it's more than, that means they cannot. They have to write separately, right? Have to write separately. And does it matter when they write together? Yeah, it should be banding together as early as possible. Okay, so from the edge, we're gonna go in, okay, and okay, from the edge, we're gonna go in, and from there, we're gonna keep going, and I'm gonna see the number of people. If the number of people is too much, then they just have to, the node has to keep go, right? Keep going. Then if they merge, we just merge the node. The number of cars, well, we actually do the number of cars. Each time we just plus the number of cars. So this, the number of cars is 1, right? And from here, number of cars is still 1. So right here, number of cars is 1. And the total of this one total is 2. And from here, number of cars is 2. So this one has to plus 2. So this one will be 4. So these 3 requires 4. That's 5. That's, these 2 requires 2, 6, 7. Yeah, so it's gonna be what's it called? Topological sort. So we're gonna go through everything. We're gonna keep count of the number of edges that's connected to each node, and then we're gonna do a priority queue with the smallest edge at the beginning. So like this 2, this 5, this 6, they will pop up first, and we're gonna do 1 car for every one of them. Right, and then they're gonna find their next, right? They find their next, and once they find their next, the next need to pop out. Wait, how do we pop this? So they float up to the top. We don't really have to, right? So we record their number of edges. And then we do that, the number of edges for -1, and then we see if it is 1, we push into the queue. If it's not, we just don't. And now we pop the queue out, the number of 1s. And then when we push into the queue, we push into the number of cars, right? And then we say, okay, how many, and the number of people in the car, right? The number of people in the car. And if it's, yeah, so when we have 3, we have 1 car with 1 person. So 3 can add it in. So there will be 1 car with 2 people, right? And then when it come here, right? When it come here, but when do we add? So 2, I go to 3, right? So that's when we add. We go to 3, 1 car, 1 people. We add the fuel. And at 3, we go to 1. We have 1 car, 2 people, we add 1. Add 1, now we have 2 cars, right? 2 cars. And 2 cars, 1 people. We only need to keep count of the one that doesn't have enough people. So 2 cars, 1 people. Now it finally comes to 0, right? It goes go to 0. So that when the 0 sees it, when it go to 0, 0 sees 0 sees 2, so I'm at 1, right? What I have is 1 car, 2 people, and then from 1 the next is 0. So if the next is 0, I push, right? I'm at 1, and then its next is 0. So I push 0. Yeah, I push 0. That's fine. I push 0 into it, and I have 2 cars. Right? I always add 2. No, we don't push 0. We already, because yeah, it depends on where do you count. Right? Where do you count? If you count at 3, when I see is, yeah, that's when you count. So you're at 0. So 0 will pop out. I see is 0 is 2 cars, right? 2 cars, 1 people. That's where 0 sees. So I need to know that trip need to add 2. And then boom, that's it. At 0, we end. So it will be something like this. Oopsie doozy, that's not it. 12. Okay, so we have n. They're gonna give us n. We don't have n. We don't. So what we need to know is there, what's it called? Egress, just edges. There are a number of edges. We'll call it edges. Okay, we'll call it edges. Counter. We also need a graph. Graph will be a default dict. But from the edge coming in, it cannot come in 2, because coming in 2, that's not an edge. But for these, they do have. So I do need to, how would you handle that? From out coming in, how do I know what's my next? Something to remove. Okay. So I need a default dict. Right, I need a default dict with a set. And I need a counter which shall count the number of edges. The number of edges. Actually, this graph shall suffice, right? For A, B in roads. Let's say graph A dot add B. Graph B dot add A. But how do you know which one has only one? So you have to keep doing all that, and then you search. Yeah, you search. Right? You search to find the ones that have only one edge. So we say one edge, so they will start with, but they don't count at the beginning, right? That's just a start. This is the next round. So we can say like 0 people at the beginning. 0 people, 0 cars. Yeah, 0 cars. So I can say Q equals, let's say for node in graph, right? If len graph node is equal to 1, which means they only have one edge, then we put what in there? We put the number of, no, the node first, number of cars, right? Number of people. Then we say while Q, okay, and then we have a result. Temp is this. Let's say for node num cars, num people in Q, right? So this is one we visited. Now as we visit it, we need to, however number of cars, because we arrive this with 0 cars, so res plus equal to number of cars, right? And then now we are at this node. The node can provide a car, but then we should decide whether the current number of cars will suffice, then we can add a car to it. Or we say if number of people, that should be 0, right? Initially, it should be 0 people. No people arrived there, right? It should be 0 people. So we should say the people is plus equal 1. So maybe it should be 0 people. Then it should be 1 car initially, right? So if it's 0 people, I add, so now we have 1 person. And I say small equal to seats, right? Then I want to avoid, I want to avoid. I guess what I can do is just if number of cars is 0, okay, say if not number of cars will equal to 1. Okay, no matter what, we'll do this. And number of people, right? And we say if number of people plus 1 is smaller or equal to seats, right? Smaller or equal to seats. Yeah, if not, we set it to 1. If it is, we don't do. If it's smaller or equal to seats, then we keep the number of cars, which means elsewise, right? If number of people plus 1 is larger than seats, number of people in the extra car, number of unfilled people. Okay, number of unfilled people is larger number of people in last car. Number of people in last car. So if number of people in the last car plus 1 is larger than seats, then num cars to the plus equal 1. We need 1 more car, and number of people this will be equal to 1. All right. Otherwise, we don't need another car. Then we say if node, right, which means node is not 0, so we haven't reached, then we say visited. Yeah, we can do that. We can do visited, right? That's the queue. If I do visited equals a set, right? For node, we first say visited.add node. Then we do this. We say if node. Then for next in graph node. If next is not in visited, I can put temp.append. Next, number of cars and number of people in last car, right? But 2 might be reaching to the same. Oh yeah, 2 might be reaching the same. Right? We can do like this. If 2 matching into the same, 2 might be matching into the same. Oh, we need to update the state. Yeah, we need to update the state. In one step, we need to update the state. Yeah, what if we have another one here that's coming here? They need to wait for everybody to come, then in order to decide, right? That's what they need to do. So no, it has to be topological sort. But to do topological sort, how do you update? I forgot how you update. So from the start, they have one edge, right? And then they visit this one edge. And then they see if it's one edge. If it's one edge, they push it in. If it's not one edge, they leave it until it becomes one edge. Which means we do need a central place to decide, right? So this is all fine, right? This is all fine. So we have this in the queue. These are fine because they have edges 1. And then we can do this. If not cars, these are all fine, right? So, but that shouldn't be happening here. We shall have a central place to say how many cars and people are in it. And then when we visit this, we gather how many, and then we decide how many shall be when they go to the next node. All right, when they visit the next node. And then when they visit the next node need to remember how many people has come, how many cars have come. And they can decide how many people to, which means all we need is just the number of people, right? That's all we need. We need the number of people. So at this, we say it's one person, all right? So we start from here, we say propose 1. And then we need to go to the next. That's when we add. And then when we, in this, we add, say we have 1 person. Now we need to check. We need to check, see my edge number. If my edge number is 1, then I'll visit this. If not, then I don't bother because someone will come to me. And then when I have the number of people, I decide how I can do the seats. Right? I decide how many cars I need. And then I will add the number of cars. And I will move on to the next. Right? When I move on to the next, yeah, that's what I want. I want to make this computation when I visit this. That's why when I visit this, right? When I visit this, I need a number of people, which is 0, right? So I don't need cars, so I don't need a number of people. So num people, right? I think that's the only thing I need is number of people, right? The number of people to arrive here, which is 0 people, right? And then for that number of people to go to the next, I can calculate it, right? So maybe I do need people map. Maybe I need this, right? So I don't need to do this. So I'm visiting this node. I know how many people is coming. Okay. Then I can check to see if we can check if we say if len graph node is equal to 1, that means I'm ready to go, right? I'm ready to go. And else, then that's that many people come to me, then I say people map node plus equal to num people, right? I just hold them. I hold them there, and I'll go to the next one. But if I have enough people, I need to go, right? If I need to go, then what I'm gonna do is find out the next one I need to go to, right? Find out the next one, and then put that into, so I say, because I only have one, so I can just say graph, so I can say next equals to list graph node, list graph node 0, right? That's the next node. And then I'm gonna go there, and that's gonna cost, and I say quotient r equals div mod, the number of people I have right now, right? Number of people divided by seats, and the rest plus equal to that number of cars plus the remainder if it's larger than 0, right? Maybe need one more car. And then once we've done that, we need to say graph next dot remove node. We need to remove it because I done that. I remove it, and temp dot append next with the number of people will come to you, right? With the number of people come to you. That's not right, because I'll get a number of people from the people map, right? I'll get a number of people from people map. I just need to go to the next. I just need to go to the next. So no matter what, I don't push the people. Okay, I don't push the people. I just push the node. I just push the node. And then I'll just push the node. And if it's 1, that's the next. Number of people shall be the people map node. That's the number of people that's been accumulating there, right? And then we'll get this, and we'll say this is the number of gas. But this is the number of gas it will take to go to the next one. That's the total number of people I have, and I'll have no more edges. I'll have 1. Then I find the next one. I get how many cars I need. This I go to the next one, and then the next one will remove me, and then I'll do this, right? This is I go to the next one. But how does the next one know how many people is going to come? I will do that by, say, people map, right? People map next will say plus equal to number of people. If I hit this node is not equal to 1, then I just wait, right? I just wait, and then q will equals temp. And of course, if node is equal to 0, right? When I say if node is equal to 0, because I already updated the result. The result is updated before we reach 0. So if node and, sorry, not 0, if node is 0, because I will add the next node to it, that will be 0, but I don't handle 0. I mean, it could be that we don't even do 0, right? Next. And then we'll do div mod, we do this, graph next, we'll remove, and then people, and we can do here, right? We can say if next we append, and then we can return res. Okay, let's take a look. It doesn't feel smooth, right? It doesn't feel like how topological sort is supposed to be done, but I forgot how it's supposed to be done. So basically I ask everybody to wait at each node until it has been cleared that I can move on. I'm not very confident, but let's see. Minimum fuel cost, roads and seats. That is not right. Num people. Oh, there's no num people. We put that many people, because there's no num people, just put that many people into the next. What the hell? Alright, that's not right. Oh, I never add one. Oh, I forgot. So people map shall equal to, oopsie doozy. Okay, so what we can fix it. We can fix it. Q. All right. For node in graph. All right. If this is equal to 1. Q dot append node people map node equals 1. Okay, and then everybody needs to be 1. Might as well do default dict. Might as well do default dict lambda 1, right? The default value is going to be 1. Then I don't have to do this. Yep, then I can return this to this q equals node. That's initial people. And then let's try these. Yeah, looks to be good. Let's try this. Oh, damn. Was all correct in the past. Now we have a error. What's that? I say graph.remove node. So node is not in there. Key error. Key error. Huh? Interesting. How does that happen? I have 0, 1, 0, 2, 1, 3, 1, 4. So we start from 3, right? There's 1. Next is going to be 1. QR is 1, rest plus equal 1. And then graph as 1, dot remove 3. Perfect. And people max, okay, that's plus that's fine. And then next one 4. And remove 4. Huh. That is interesting. Which one? Which one has issue? Which one has issue? So I probably need to print. Let's print graph at every stage. Graph node. Okay, so we start right with node is 2. Oh, node is 2 is fine. And 2 is 1. Blah, blah, blah. 2 is okay. 0 don't really care. Oh, 0 does remove. 0 does remove. Wait, hold on. Oh, 0 does remove. But it's okay, right? 0 remove. Next one's 3. Next one's 4. And the next one is 1, because 1 only has 1. And then I done it. And then, ooh, why do you do 1 again? I'm at 1, okay? And then, if I am at 1, which, no, the length is 1, next is going to be 0, right? We do whatever this do, graph next, remove, it's perfect. And then if next is 0, so if next shall be, oh, 1 got to push in twice. Because 3 and 4, 3 pushing 1, 4 also pushing 1. I only needed to be pushed once. I only need to be pushed once. Okay, I only needed to be pushed in once, because at each level, yeah, because I used this. I used this people map to aggregate the people, so the queue can actually be a set. The queue can be a set. And this one just add. The queue can be a set. That should be 4. Okay, let's try. I'll do this. Yep, should be 4. Okay. Oh my god. Wow. Red alert. This is bad. What the hell? Three. Oh, the edge case. Interesting. How's this one wrong? All right, I need to let's do it again. Print Q. Not Q. I need graph node and graph people map and node. Oh, there's no node. Graph and people map. So is this one defined right? Okay, we'll do graph. And for, I don't know, A in graph, print people map A. Okay, so we start with this, right? 1 has 2 nodes. 0. Oh, bonkers. I think I put 0 first, maybe. If node and yeah, I think I put 0 first. Should not put 0 in there. Okay, if node and Jesus. Boy, this is bad. Dude, this is very bad. How? It's... I mean, what we can do is we can just say if node in graph next, if that's the issue, but that doesn't solve it. 28. That doesn't solve it because I never really think it's possible. Yep, should be 22. So that's not the way to go. You shouldn't be waiting for everyone to join you. Huh? You shouldn't be waiting for everyone to join you. Why would you not wait for everyone to join you? Now, there's something wrong. We shouldn't need to do this. Because I already said graph node, right? Next is equal to graph node 0. Which means node has a connection to next. How come the next doesn't have connection to node? Something is not right. Something is not right. I don't think this is necessary. Which means we have an issue. Which means we need to investigate. But Lord, this is a large thing. But don't worry, we'll figure it out. Let's go graph. We need to know the node. Oh Lord. 4 appears twice. That's okay. That's okay. Because I actually should put it inside. Four appears twice. How is that possible? How is that possible? How can 4 appears twice? So we add node 4. 4 has connection to 3. 3 has connection to 4. So 4 removes 3. 4 need to remove itself as well. I forgot to remove itself. And then somebody has connection to 4 as well. Wait, hold on. I think it's because... Wait, let me think again. So we start from outside, right? And they come. And then remove. then they shouldn't. How is that possible? Look, we have 19 has connection to 4. 5 has connection to 4. 8 has connection to 4. 7 has connection to 4. They all have connection to 4, but they have been visited before. Yeah, they have been visited before. So I'm now at 4. Then I go to 3. 3 only has 1. But 4 comes out again. Because 4 was in. How is that possible? The Q is a set, right? The Q is a set, which means if oh wait, hold on. Hold a second. So first of all, let me remove this. There's a little bit clutter here. Okay. Where's the Q? Jesus. That's the Q. All right? Q is all of these. And then we handle 5, 6. Okay, so actually let me as well do this. Okay, so Q is 3, 4. Q is 8, 16, 4. That's fine. Q 8, 16, 4. So we do 8, we do 16. When we have 4, we find out 4 has 1, right? So we push 4 in. But at this time, I do 8. I do 8. I shall only push it in if it has 1. Shouldn't check here. If next, and just follow this. Len next is equal to 1. Then I go. No, of course this is wrong. Then we good. Has that been going too fast, or I don't know. It's not easy. That's not easy. Not a difficult problem. And to make it so complicated. What the hell? Seriously, what the hell? You just follow. You just follow the logic. You have the logic here. I don't understand why you don't follow. And in fact, if you do this, you might not even need to use a set. Right? You might not need to use a set. Why would you need to use a set? Because you don't want, but once it's ready to be pushed in, oh, you might still have multiple. If you have multiple, but that's fine. If it's multiple, it's only when you get to 1, which means this is not necessary. We can do it with a list, which can improve on the performance. I don't understand why you didn't think about all this earlier. Make this one so much more complicated than it's supposed to be. Look at our track record. Our track record is good. 3 errors. Right? I don't understand why you just can't do it previously. It's just a BFS. I don't understand. I mean, I was tired and a little bit sloppy today, I gotta say. 2477, because we had a great day today. We went to see Mount Diablo, a topological-ish sort. We use, so the idea, right, the core idea is to hold all the people at one city, at one node, until this node has only one outgoing edge. Then we decide how many cars are needed to maximally, to minimally, to how many cars are needed to decide the minimum number of cars, right? Decide the min number of cars needed to transport all the people. This is a tuple. This requires a BFS, right? That only pushes a new node to the queue when that node has one edge. Thus, the graph we create use set to hold all its neighbors. We will update it as we visit, right, a new node. We also use people map to keep track of the number of people that have arrived at a city, at a node. Yeah. Well, O(n) plus e. Each node got visited once. All right, let's see. O(n). All right, let me see what I did in the past. I have 4 in the past, including this one. 131 test case. Okay, so this is the earliest graph. Land children. I use heap. Number of children. I'll pop. If degree is not equal to, I continue. Otherwise, that's plus equal to, and for child in this people child. That's my people map. Plus equal to that. Graph does not remove. If child, I pushed it in. So I use that to get the smallest child out. And I use this to handle any mismatches. So yeah, that's a topological sort as well. Yes. Yes, but I use the same, but I'm faster than this one. So I keep reading. Oh, go from capital out. I probably do it. This is a BFS. Oh, hold on. This is my solution. Use ceiling is, yeah, should use ceiling. Child is the next, yeah. If child, people child, plus equal to this. Well, I don't do the if child early. If this and graph.child, graph child, see, graph child.remove. I do this plus, yeah, I mean, it's fine. We just don't handle 0. And I delete the graph. That's not necessary. So, okay, so this is actually not bad. This is topological sort. So the only thing that I can improve is don't use this. Okay, so we don't use this. Res plus equal to, yeah, it's mass.ceiling. Mass.ceiling people map node divided by seats. Yep. Update. Use mass.ceiling. Yeah, it is topological sort. All right, I'm gonna check the other solution. Man, it's gonna take so long. I thought. Oh. Might be faster. Yeah, slightly faster. I think it's just because ceiling. Okay, so next question is, what is the DFS? Oh, yeah, I see. That's exactly what we do. At each node, one find a total, and oh, so much easier. Damn. DFS is easy. DFS. Right. What solution 1 does is to compute for each node the total number of children it has. This can be easily accomplished via DFS. Okay, so we'll get the graph. Okay, we actually don't even need a set. I think a list will do. I seriously think a list will do, right? And then we'll do DFS. So for each one, we just need to compute the total number, and then we'll report to the result. So we have a node, don't return anything. All right, a node will be an integer. And then we say if node. Not really. I want 0 as well. So I just want to know the total number of my subchildren. So I need to return something. I need to return the total number of children. Okay. Then we're gonna say total equals 0, right? And then for child in graph node, I'll say total plus, maybe we can just say total equals sum. DFS child in graph node. Oh, but it might be able to go backwards. Have you thought about that? Right? Have you thought about that? So I think we do need visited. So equals 0. Do this. Child in this. Now visited.add node. If child is not in visited, total plus equal to DFS child. Right? So once we are done, we have the total. And total shall be 1 because I need to add myself. Then what? Then I need to say if you think about it, if the node is the end node, right? and I have one person. So we say if that's the end node, and I have one person, I say I'm going to shift this one person. That's how many would it cost. And then here I shift that many people. And at node 0, I say I have that many. So we have to say if node res self dot res plus equal to mass dot ceiling total divided by seats. And then we call DFS on 0, and then we'll return self.res. Oh, I forgot return. Yep. Yeah. Very similar, huh? Very similar. All right. That's way longer than I'd like, but I don't know. I didn't have a good thinking today. Anyway. All right, I'll see you guys tomorrow, where I will have to read the hint. Maybe I should read a hint tonight. Think about it, and we'll do it tomorrow. All right, I'll see you guys tomorrow.